So, let us once again quickly recap where we were. Okay. So, we are looking at the Gallagher A decoding algorithm. Okay, it is a hard decision decoding algorithm over the binary symmetric channel. Okay. So, what are the various features if you think about the way it is working? It is hard decision decoder. Okay, it works over the binary symmetric channel. It is iterative. Okay, the iterations are in 2 steps. First step is row processing. Each iteration is split into row processing and column processing. Okay, the basic idea is to use the rows of the parity check matrix that are connected to a particular bit to get estimates of that bit. Okay, so there is an incentive directly from this algorithm to make sure that no 2 rows overlap in more than 2 places in once, right, more than 2 once, right. So, if you do that, you see that your row processing information is independent, at least for the first iteration. Okay, so beyond that it just becomes a little bit more complicated to figure out all that was involved in a particular estimate. Okay, so because what you do is you iterate on those estimation, right. You first get some initial estimate, then you use those better estimates to rederive the estimates and you keep continuing. Okay, so it becomes a more complicated process to visualize what is happening iteration after iteration. Okay, so I will make one brief attempt at it and then we will move on to the Tanner graph. Yes.
One node.
In more than 2.
No, it shouldn't be.
Oh, more than 1 you saying. Okay, more than 1, I am sorry. Oh, more than 1. Okay, more than 1, is that correct? Okay. So let me just briefly show you one picture with the parity check matrix to see how this how multiple code words of the dual or more code words of the dual than that are there in the parity check matrix itself are being used in the decoding. Okay, just to illustrate real quick, and then we will move on to the Tanner graph description, which is much more standard and much more useful and interesting. Okay, so let's look at the parity check matrix, and maybe I will rearrange the rows so that the ones of the first column show up in the beginning, and maybe the ones that are here I will use, let us say WC equals 3, WR equals 4, okay, just to make it a little bit more. Okay, so everything else is 0, so it is a huge matrix. Think of it as some very big matrix. So this could be one way in which I can permute the rows and columns and bring everything up here. Okay, so I can do this, there is no problem. Okay, so what happens in the first iteration? You get an estimate for, so this is of course R1, R2, R3, R4, R5, R6, R7, R8, R9, R10. Okay, so R10 comes all the way down here. Okay, so in the first estimate for R1, the received values involved are R2, R3, R4, and the code word of the dual involved is simply the first row. In the second estimate, the code word that is involved is the second row. In the third estimate, code word that is involved is the third row. Okay, what happens in the next iteration? Okay, so it is a bit more difficult to imagine, but let us say I look at the column corresponding to I look at the second column corresponding to this guy. Maybe I put the ones right here. Okay, right, and maybe the remaining ones for this, maybe I mean I will just draw it far away. I mean it could overlap maybe with here, but I will draw it far away so that we see it a bit more clearly. 1 1 1, and then next one is maybe 1 1 1. Okay, so these are additional values here. Okay, now what would have happened in the first iteration for C2? What would have happened? It would have got estimates from the first row and then yeah, fourth and the fifth row. This is for C2 in the first iteration. Okay. What happens for now C1 in the second iteration? Imagine what is happening. See, so you are going to update that depending on the these two things. Okay. So, the estimate for R2 now, so C2 that you got in the first iteration, there were 3 different estimates, one from the first row, another from the fourth row, another from the fifth row. Okay. When I update the estimate for C2 that is going to be used in the second iteration in the first row, what will I do? Based on these two guys, right? These two guys will play a role and R2 also will play a role. Okay. All right. Now, when this updated value estimate is being used in the second iteration for C1, what is actually happening is indirectly you are using the fact that the first row XORed with the fourth row is also a code word of the dual. Okay. So, what is that thing that you are using? 1 0 1 1 1, which is the XOR of first row and fourth row, right. That second estimate that you had, the estimate from this row, from the fourth row that went into R2 will make its way to R1, and that is almost like, I am sorry, 1 0 1 1, okay, that also is involved. So, it is almost as if you are getting the estimate from this code word, okay, but it is happening indirectly in an iterative way. In the first round you only get estimate from fourth row for R2, and then in the next iteration you are using that new estimate in updating the estimate for C1. So, indirectly the code word that is involved is 1 0 1 1 1 1 1. Notice this 0 here is crucial, so that you do not use the same R2, okay, so you cannot use it again. Okay. So, of course, in the hard decision decoder it is not very easy to make this connection explicitly. In the soft decision decoder you can make an explicit connection like this. Okay, we will see a soft decision decoder later. There you can make a very explicit connection between these XORed code words and what is happening in the iteration. But essentially this is what is happening. So, you are using more code words from the dual indirectly through the other bits that are getting updated in each row. Okay, you are using this row, but then the values you use for those rows, the other bits are getting updated through other code words, and essentially you are using the XOR finally. Okay. So, this is what I briefly meant when I said even though you are using only the rows in the parity check matrix explicitly, there is implicit use of XORs through this connection. Okay. When think about it, it's kind of a loose connection at this point. Maybe when we do soft decision decoding later, we will write down some explicit expressions. At that point you will see this code word is also involved. Okay. Is that fine? Think about it. It's a bit rough, I know, but it's important to keep in mind. Yes.
You're taking fourth and fifth row effect together also, so it's not XOR of first and fourth.
Exactly. So, this other code word is also involved. You are right. Yeah. So all these code words are involved in that decision. That's all I am saying. Okay. So, all these other code words are indirectly involved through R2. Okay. So, when you write the soft decoding expression, you will see every extrinsic information will get added. So, it will be much more clear. Here we are not writing any soft LLR, right. So, it is only just estimates. So, more and more code words are involved, that is all. Okay. It will not actually be 1 1, I put 1 1 here, but this is a bit questionable because again you are using more code words that R3 is connected to, okay, right. R3 is connected to 2 others, those also are giving some estimate, that is what you are actually using. Similarly, R4 is connected to 2 others. So, you are using a lot of things at the same time. Okay. So, even though it looks like in the first iteration I am only using very small number of code words, the number of code words I am using eventually from the dual increases in fact exponentially with iterations, and as you do more and more iterations you are using more and more extrinsic information and all that gets added up. Okay. Of course, the independence assumption is crucial. We are using the independence assumption, it may not be valid, but even then it is something. Okay. So, this is the brief idea. With the Tanner graph this will become a little bit more clear. Okay. So, maybe for now it's a bit hazy. Okay, so now let me move on to the description using Tanner graph. Okay, so the algorithm that I described, Gallagher A algorithm, of course Gallagher invented it. He came up with it in his PhD thesis without any reference to the Tanner graph. Okay, so all these ingredients were already there. How you should not use this information from the same row in the next iteration, etc. Okay, all that was crucially there. Okay, so now the modern way of describing this algorithm is of course using the Tanner graph, and there you use this notion of what's known as message passing. Decoders on Tanner graph. Okay, so the same Gallagher A algorithm can be interpreted as what's known as a message passing decoder on a Tanner graph. Okay, so all this confusion I had in describing to you the estimate of this based on that, and then you have several other estimates for each thing, you have different estimates, etc., can be very nicely phrased in the Tanner graph language, and you will see it's very simple. All you have to describe is what are known as local operations, then the global operation kind of gets defined automatically without any problem. Okay, so that's what's nice about the Tanner graph. You have some local view, global view, etc. So we'll write it down, we'll analyze it, and we'll finally slowly get to the main result. Okay, so what are these message passing decoders? Okay, so let me have the right page up there. Okay. Okay. So once again, remember it's BSC, and the received vector is over a binary symmetric channel, and we are doing hard decision decoding. Okay, so I'm only going to describe Gallagher A right now. Okay, so you might there are of course message passing decoders are very general. There are several ways of doing it, but what I'm going to describe is the Gallagher A decoding algorithm as a message passing algorithm. Okay, so remember the parity check matrix I drew has a Tanner graph representation. It has bit nodes, n of them, and it has check nodes as many as the number of rows and all kinds of connections. Okay, so if you think of what's happening in the first step in the Gallagher A decoder and multiple iterations, essentially what's happening is you have a bit node and it's connected to WC check nodes, right. So you have a particular bit node, and let's say the ith bit node, it's connected to WC check nodes, right. Any processing that happens, the row processing or column processing, row processing for the ith bit node for instance, involves these WC check nodes, right, and the column processing for the ith bit node also kind of involves the same picture, right. So it's not is that correct? Is it clear? Do you see what I'm saying? Okay, so essentially all the estimation and iteration that's happening is mostly local. It's around this bit node. Okay, you don't really do any operation that is far away from the bit node. You only see close to the bit node and use the rows directly connected to it. Okay, by updating these messages and then passing them around, you indirectly use the remaining part of the graph. Okay, so directly you use only the local things. Okay, so you will see the entire Gallagher A algorithm can be given a simple local description, okay, through this message passing idea. Okay, so we will always think of messages flowing from bit nodes to check nodes, and then there will be messages that flow from check nodes to bit nodes. These messages will basically be estimates of the ith bit node. Okay, that any message that flows on this, okay, will be estimates of ith bit node. Okay, so this is the crucial idea in a message passing interpretation, okay, which is what happens even in the Gallagher A decoding algorithm. You are mostly concerned with estimates for a particular node, and when we describe it in the Tanner graph language, we will talk of messages that flow from bit node to check nodes and messages that flow from check nodes to bit node. Okay, any message flowing out of the ith bit node will be an estimate for the ith bit node, ith bit. Okay. Any message that is flowing into the ith bit node will once again be an estimate for the ith bit. Okay. So, that is the main idea to remember in this description. When I describe it, if you remember that idea, many of the things will be very simple. Okay. You can also describe it in the matrix language, but it is a little bit more involved. So, best thing is to do is the tanagraph. Is that all right? Okay. So, let us first do the first iteration. Okay. Iteration 1 is a little bit special because you do not have any extrinsic information. Okay. I will draw the ith bit node. Okay. This is the ith bit node. Remember, this is the first iteration. The only thing estimate I have for the ith bit node is Ri. So, this Ri is simply associated with the ith bit node. Okay. And now this guy is connected to, let us say, as many check nodes as you want. In this case, we have been looking at WC check nodes. Okay. So, in the first half or the row processing step, or let me not say that, in the first, to initiate the decoding, some messages to flow in this tanagraph, right. So, you have estimates for bit nodes on the left side, which is just Ri. Now, if I want to simply pass this message or pass this estimate out to the check node, okay, what is the only thing I can do from the ith bit node? I can pass Ri. So, what will happen in the first iteration is simply Ri will flow out of each of the ith node into the connected check nodes, each of the ith bit nodes to the connected check nodes. Okay. So, it is a very local simple description of message passing or estimate passing from one side to the other. Okay. So, this is like the first half of the first iteration, okay, where messages are flowing from the bit node to check node. These are estimates. Okay. All right. So, now in the second half, okay, what will happen is you have a check node, let us say the ith or jth check node. Okay. The jth check node will now be connected to how many bit nodes? There will be WR bit nodes, right. So, it will be connected to all of that. And let us say, just to make the notation simple, I will number these bit nodes as 1, 2 all the way to WR. Okay. It will not be numbered from 1 to WR. Okay. Of course, it will depend on J, right. So, if you want, you can call it 1 of J, 2 of J, etc., but people do not like such things, or maybe J1, J2, etc., whatever you want to call it, but to simplify notation, I will simply say 1, 2 all the way to WR. Okay. These are the bit nodes that it is connected to. What would have happened in the previous step? Yeah, R1 would have flown from, not flown, would have been passed from 1 to this check node. Okay. R2 would have been passed from this thing and so on, right. So, this is what would have happened in the first iteration. WR would have passed from this guy to this guy. Is that okay? So, what will happen in the second step of the first iteration is the check node will now pass back estimates for each of these bits. Okay. So, remember what has to flow on this edge, the first edge here, it has to be an estimate of bit 1. Okay. It cannot be an estimate of bit 2, bit 1 has to flow. What about this edge? Estimate of bit 2. Okay. But this check node now has two different estimates for bit node 1. What are the two different estimates? One is R1 itself, the other is XOR of all these other things, R2, XOR, RWR. What do you think it should send back? It should send the XOR, no point in sending R1 back, right. R1 already bit 1 has, why will I send R1 back? There is no reason why you should send that. So, that is some kind of, that is what is known as an extrinsic principle in message passing. Okay. Whenever you receive something and whenever you want to send something back, you do not repeat that information. Okay. You do not resend that information that you got from a particular node. So, this is kind of a principle that is followed in most message passing algorithms in general, and that is something we will again repeat here, and it is very similar to the estimate that we did in Gallagher A matrix description also. Okay. So, what will be passed back here is R2 XOR, Okay, so maybe this arrow is kind of misleading. Okay, what will be passed back in this is R2 XOR X3 XOR R2 XOR R3 so on till RWR. What will be passed here in this direction basically is R1 XOR R3 XOR so on till RWR. What will be passed back here is R1 XOR R2 XOR so on till RW R minus 1. Okay. So, the nicest thing about this graph picture, you can see what is nice. All you have to do is give local descriptions. Okay. You do not have to remember this huge matrix and worry about what is happening at the same time everywhere. Okay. And simply say you give the local description and say you repeat this for each check node. It is very easy to do. Okay, right. In the first step you repeat for each I. Here you repeat for each j. That's it. So, that is enough to specify what is happening here. Okay. And that is exactly what happens in the Gallagher decoding algorithm also. Okay. So, kind of the first step maybe was a little bit hidden. Okay. So, I did not state it explicitly, but this is what you do in the first step. Okay. Is it clear? Any doubts or questions?
XOR of everything.
XOR of everything to what?
R1 to R omega.
Oh, you send that to 1 and then
So
let
everything.
1 figure out the XORs subtracting the R1s, is it? Yeah, you could do that also. So, of course, so this point is where do you want to send WR different things, all you have to send is R1 XOR R2 back, yeah, it is perfectly correct, and then let the each bit remove its own thing and then figure out what it is, that is also perfectly fine. Okay. So, that is fine. So, those are ways of implementing this in a more efficient way that you can do. Okay. So, now comes the description for iteration L. Okay. So, I will give a description for iteration L, which is a general iteration. You can think of L equals 2, 3 so on. Okay. For 1 of course, you have to use the previous description. For iteration L, you have to do this is the description that I am going to give. Okay. Okay, so you have so what has happened before. So if you look at the particular bit node, the ith bit node, it has its intrinsic information Ri. It is connected to WC check nodes, which I will for convenience number simply as 1 to WC, it is connected to that. What would have happened in iteration L minus 1 at the very end? Messages would have been received from each of these WC check nodes. Okay. So, I need some notation for it. So, I will simply denote them as can't remember if I should use U here or V here. What should I use here? I should use U. Okay. So, I will use U. So UI L minus 1. Okay. So I do not need these i's, I think it is just the ith node. So, simply say U1 L minus 1, U2 L minus 1 so on, UWC L minus 1. Okay. So, those are estimates that would have been received in from the previous iteration, right. I can always assume that some WC estimates are being received. Each of them, remember, are estimates for the ith bit. They are all extrinsic estimates. In addition, I also have the intrinsic estimate Ri. Okay. What I have to figure out is what I will send back. Okay. So, what I send back, maybe I will denote it as V1 L, V2 L, VWC L. Okay. And how do I figure out V1 L? I will tell you how I figure out V1 L. If u2 L minus 1 equals u3 L minus 1, so on till uwc L minus 1 equals some b, then you set v1 L to be equal to b, else v1 L equals Ri. That is the rule for v1 L. What will I do for v2 L? If u1 equals u3 equals so on till uwc equals b, then you set v2 L to be equal to that b, otherwise you set v2 L to be equal to Ri. That is it. Okay, so as simple as that. It is the local description. Of course, you repeat this for each I. Okay. Is that okay? So that is it. Okay, I am writing it only for v1. So hopefully everything else is also clear. For everything else you have to do the same thing. So once again the principle is, we are following the principle. The principle is to not send known information back to the same node. You got u1 L minus 1 from the first check node, no point in using that and sending anything back. Okay, so you do not do that, because you have to maintain the extrinsic nature of all messages that are passed. Okay, you do not pass known information back. Okay, it will only cause some kind of feedback, negative, positive feedback, and blow up things, etc. Okay, so you can use the systems description to motivate that. Okay, so hopefully that's clear. This part is clear. Okay, the next step, what happens? You have to now look at the jth check node. Okay, which has WR bit nodes connected to it. Let us say this is the jth check node. So it is very simple. The check node operation is much simpler here. Okay, this would have been, this will receive. So with some major abuse in notation, I will simply say this is v1L, this is v2L, this is vwrl. Okay, so of course the index is not the same. You have to worry about which bit node is connected to, etc., but just for simple description, I will simply say the messages that are received from the corresponding bit nodes is this. Okay, what are these messages? Once again, remember, these are all estimates for the corresponding bit. So v1L is an estimate for bit 1, v2L is an estimate for bit 2, etc. Okay, that has been received in the lth iteration. Now this thing will have to send back u1 L, u2 L, and so on, uwrl. Okay, what will this be? What will u1 L be? It will be the XOR of v2L, v3L, so on till vwrl. Okay, so likewise for u2, u3 and all that, u2L will simply be v1L XORed with v3L, so on till vwrl. Hmm. Okay, so then that is Gallagher A prime, or maybe it is Ashwin Ram A or something. So this is Gallagher A. Okay, so of course, I mean, like he is pointing out, his question is, can you not change any of these things? Of course you can change any of these things. Okay, as long as you can get good performance for the decoder, that is great. Okay, and there are all kinds of research, believe me, in the last 15 years there have been 10,000 papers on this. So every single thing has been tried. So it's very unlikely that you can try something new. I mean, unlikely only, still possible, but unlikely that you will come up with something new. So many researchers have looked at it. It's in the standards, right? So people have tried everything literally. Okay. Yeah, but of course you can try variations here. So this is the rule that it's called Gallagher A. Okay. Any questions? So let me just ask a general question now. Which one do you like better, the matrix description or the Tanner-graph description? Tanner-graph description is much more natural, more intuitive, simple, and it's easy to implement. For instance, so many things you can do with the Tanner-graph. and it is more difficult to visualize what is happening in the matrix. Okay, so this is much better.
Sir, are there any convergence proofs at least for the ML case? Converges to a particular code word?
Okay, so that's the next question is about analysis. You're saying, okay, you've described the decoder. How good does it do? What does it do? For instance, it's not even clear what it does. I mean, it seems to be doing sensible things locally. Will globally anything good happen? I mean, it's an important question, right? So you have to ask that question. There are partial answers, partial very successful answers. So these answers can be used for designing codes and they work very well. Okay, there's no complete answer. I can tell you very easily, and anybody can tell you. There's no complete answer saying these are the received errors that can be corrected. These are the errors that cannot be corrected. No such answers. Okay, and since the partial answers are very successful, not many people are looking at complete answers also. Okay. Anything else? Any other question? Okay. All right. So now we'll slowly move towards analysis, but let me reiterate once again. In this Gallagher A message passing algorithm, messages are flowing on the edges between the bit nodes and the check node. Any message that's flowing on an edge is an estimate of the bit node that it's connected to. Okay, in both steps, right? Whether it's the bit, whether the message is flowing from bit node to check node, or from check node to bit node, it is always an estimate of the bit node that is connected to. Of course, there's no point in estimating the check node because it's anyway it's not transmitted, right? So it's not desired. So you always estimate the bit node. That's one thing to keep in mind. Okay. The other thing to keep in mind is the extrinsic nature of the messages that are passed. Okay, so you, as much as possible, locally at least, you avoid resending information from the node that you received. Locally you avoid it. Okay, globally of course there is no way to avoid such things, right? Finally that message would have made its way through some other loop and finally come back here. You can't avoid that, and you don't care about it. Okay, you don't care about it. Locally you avoid sending back information. Okay, so I'll try and depict that in some plot here. Okay, so that's the other thing. The third point, if you want to look in terms of code words of the dual, right? If you want to think about code words of the dual, what the message passing algorithm is doing is it's specifying some kind of a sequence in which you process code words of the dual. Okay, so that's what it's doing at the end of the day. Of course, you don't process them ideally, you process them approximately, assuming they are independent, but it gives you a sequencing of the code words by which you process the code words of the dual. Sequencing of the code words of the dual by which you process for information, and it's not the same sequence for every bit, right? Every bit depends on its neighbors, and then it depends on the neighbors there, so on. Okay, so the neighbors play a big role in defining how the code words are processed. Okay, so for instance, the first iteration, the immediate neighbors of the bit node. What do I mean by neighbors? Yeah, so the nodes that they are connected to immediately. Okay, so only those nodes are involved in the first iteration, and then the neighbors of the neighbors are involved in the second iteration, then their own neighbors are involved. So you are exploring this entire Tanner graph one neighborhood at a time. You go to the neighborhood, and then neighborhood of the neighborhood, neighborhood of that neighborhood, and you are assuming there will be no dependence in any of these neighborhoods as you keep proceeding. Of course there will be, I mean there might be some dependence, then you will make errors, but you live with that. You say, okay, fine, I make errors, I don't care, we will see how it works. Okay, so that's the general idea. So one thing I will strongly urge you to do is to write some simple Matlab programs. It doesn't take more than 10 lines for many of these programs. Okay, one program is to generate a 3,6, for instance, matrix for a given block length n. Okay, for instance, if 6 divides that n, then it's very easy to do the Gallagher construction. It's almost trivial to do it. Okay, just pick an arbitrary permutation, try your best to avoid overlapping of rows, but even if you can't avoid it, let it overlap, it doesn't matter. You just have one realization of the parity check matrix. It's very important. Unless you do this, you will never believe it, okay, because I will never be able to show that it really works. Okay, I can only give you partial results. Based on that, if you want to really believe it, you have to work with it. Okay. So you come up with parity check matrix, and then what can you do? You can simulate the BSC very easily, right? It is very trivial to write a Matlab program to simulate the BSC, and then you run this decoder. Okay. This decoder is very easy. So in fact, if you remember the parity check matrix, all messages correspond to positions of ones on the parity check matrix. Remember, all messages are being exchanged on the edges. So all you have to remember is this big sparse matrix, then all your messages will be on the sparse matrix. Okay, so only those locations will be passing messages. So it's very easy to write the program. You can write it in like 10 lines in Matlab and run this decoder. Keep iterating it, change your probability of error and see what happens to the probability of error after your decoder. Right? You have to do it, and unless you do that, you will not really learn how these decoders are working and how they make errors, what is going on, etc. Okay, and unless you do it, it's very hard. Is that okay? All right. So of course I have done this before. So let me show you what I got. Or maybe I should import it from there. No, so that's a better idea. So anyway, you can see it here. So can you see it? See it reasonably clearly? Okay. So there are different colors. So how do I do full screen? It's play slide show. Is that full screen? Will that do that? Hey, what is this? Okay. See, pause it, is it? Okay. But there's only one picture, no? It will take some other picture from the same directory, is it? Okay. Be very careful with Windows, you know. Okay. All right. So this is what happens if you try and do what I said. You generate parity check matrices from the Gallagher ensemble. I don't know if I did Gallagher. I don't think I did Gallagher ensemble. I did socket ensemble here. Of course, I also took care to avoid overlap of rows in more than one position. I have done both for these things, and then that's 3, 6 regular. What's plotted on the x-axis is transition probability of BSC. So as you go to the left, it becomes channel becomes better and better. Your performance should improve. Y-axis you have bit error rate. Okay, I don't know if you can see the numbers very clearly. Its font is not very big, but it's logarithmic. It starts with 10 power 0 and then goes to 10 power minus 1, etc. So is the x-axis. 10 power 0 is all the way on the right. Then you have 10 power minus 1, 10 power minus 2, 10 power minus 3, so on. Okay, and there are different colors. First of all, there is this vertical line which is marked threshold 0.04. I will describe that later. I will tell you what happens there later. But there are other lines. There is a blue line which is for n equals 30. Okay, I don't know if you can see that legend up on top very clearly. It's n equals 30, and then the red line is for n equals 100, and then you have the green line which is n equals 1000. And at that point you can see it's quite good. You know, I mean, it's pretty good code. When you have 10 power minus 2 of transition probability, you are getting bit error rates down to close to 10 power minus 6. Okay, so it's not bad. And when you go to 10,000, it's even better. Okay, and then there is this threshold which is analysis, which you can approach if n becomes technically infinity but large enough. Okay, so even for 10,000 it's fairly close. I mean, it's come very close to the threshold. Okay, and we will see how to compute this threshold. It's quite easy to do that. We will come up with, well, easy to compute, maybe not very easy to prove, but very easy to compute. Okay, I'll show you how the computation is done. Okay, so a plot like this I would urge all of you to recreate. Okay, so you'll really learn LDPC codes if you do this. Okay, at least for the BSC. Okay, and then you can slowly modify other things later on. Okay, any questions?
Itself is not based on anything that's specifically for what kind of channel exists. It's an algorithm that is.
Well, it's okay. The question was if the algorithm is for a specific channel. Okay, so it's a hard decision decoder, definitely. So I guess BSC is a natural assumption. But if you put AWGN and then you'll have to run the slicer first and then do this. So we will soon see a soft decision decoder also, but this is the hard decision decoder and this is how it works. No questions? Happy? Okay, so this is how it does, and does quite well. Okay, so this, remember, this is rate half code. Rate half code, the what's known as capacity for BSC is 0.11. Okay, so what it means is, if you have a rate half code for large enough n, any p less than 0.11, you can get technically 0 probability of error. Okay, well, very close to 0 probability of error. So 0.11, where will 0.11 be? It's this guy, right? So roughly 0.1, so that's 0.11. This threshold is 0.04. Okay, so it's saying basically below 0.304, I'm going to do well. So it's a little bit away from capacity, and it's difficult to actually build LDPC codes which will get very close to capacity for BSC. Okay, so even after so much research, nobody has shown you can get really close, but you can get quite close with other kind of LDPC codes. These are regular LDPC codes. If you do irregular, you can get a bit more to the right half. Okay, so what we are going to see next, maybe very quickly, is to how to compute this 0.04 for a Gallagher decoding algorithm. Okay. Okay, so how do you compute that that number threshold? Like I said, the threshold has proved to be a very valuable calculation in the design of LDPC codes and simulations. I mean, in optimization of LDPC codes and getting good performance, etc. But there are some limitations in its definition. There are some assumptions, and but you shouldn't be discouraged by it, because it's a very valuable tool. Okay, it has really driven the development of LDPC codes. Okay, so the main idea here is, you will define. So you remember, this is my general description of the decoder. Okay, I will try to track the probability that a particular message that is passed is in error. Okay, so what do I mean by in error? So first thing I'll assume is all 0 code word was transmitted. Okay, so that will be the first assumption in the analysis. So this is threshold analysis. Okay, so it's also called density evolution. So I think density evolution is probably a better description. Okay, so I will define. So the way I have defined it here, I will define PL as the probability that VL equals 1. Remember, what is VL? Maybe I should draw that. Maybe I should capture that and draw it here. Okay. Okay, so this guy is VL. It's the message that is passed. This is a message passed from bit node to check node in iteration L. Of course, it's a random variable which denotes that message, and I am interested in the probability that VL is equal to 1. Okay, remember, my assumption is all 0 code word was transmitted. Okay, I have assumed all 0 code word is transmitted. So this probability is some kind of a probability of error. Okay, for instance, if I show that this probability is 0, then what happens? All the messages V that were passed are zeros. So what will happen? Remember, in the next step of the iteration, if all these things are 0, everything that is passed back is also 0, and I would have decoded to the correct code word. Okay, so it makes sense to look at this probability in the all 0 code word case, probability that VL is equal to 1. Okay, so of course it depends on the probability that RA is 1, and it also depends on the probability that the U's are 1. Okay, so what I will do is I will define a QL, or maybe a QL minus 1, which is the probability that UL minus 1 is one. Okay. So, I want to look at the probability that VL is 1. Of course, that will depend on probability that these guys are 1. Okay. The crucial assumption here is that U1 L minus 1, U2 L minus 1, UWC L minus 1, all of these guys have the same distribution as this UL minus 1 and they are independent. Okay. That is a pretty important assumption, as is the all 0 code word assumption. Both of those are important and all these can be justified. Okay. I will maybe not be able to fully justify it, only partially justify it. In fact, it can only be partially justified, but it's still a useful tool. Okay. So, we will assume all that. Okay. So, is that clear? So, I will think of a VL, which is a random variable which denotes the message passed from bit node to check node in iteration L, and my assumption in the analysis will be V1L, V2L, VWCL, all of them are IID according to VL. Same is the case on the other direction. Okay. UL will be the message that is passed from check node to bit node in iteration L, and whenever I have U1, U2, UWC, they are all IID according to that same distribution. So, QL minus 1 is that probability, PL is that probability. Okay. Remember, we also have the transition probability on the channel P. Okay. BSC P is there. That is the probability that Ri is equal to 1, that is P. Okay. So, now I have the rule for finding V1L from U2L minus 1, UWCL minus 1 and Ri. Okay. If I look at that rule very closely and analyze it, I will get the following equation for PL in terms of QL minus 1. Okay. So, I am not going to describe a proof for this, it is quite easy, but it does involve some thinking, but it is not too difficult. Think about it and work it out for yourself, only then I think it will be very clear to you. Okay. So, you can see based on our rule. Okay, what is our rule? If you want, I will reproduce that rule for you. Okay, so that is the rule. Okay. If all of these guys agree to a particular value, then that will become that value. Okay. Else we will set it to Ri. Okay. So, you can look at this rule, stare at it very closely, and you will get this inequality. Okay. This equality. Okay. So, go back and think about it. I am not going to describe this in much more detail. It is a simple probability computation. You can think about this. Is that okay? So, you have got PL in terms of P and QL minus 1. Now, you have to get QL minus 1 in terms of PL minus 1, and that is not very difficult because that is simply a XORing operation. I am going to assume it is independent. So, you can very quickly show the following inequality, that QL will be equal to 1 minus 2 PL raised to the power WR minus 1 divided by 2. This you can show just based on the XORing property. Okay. Is that okay? So, this is the basic density evolution analysis. So, you have random variables which denote the messages that are being passed, and you track the probability distribution of that random variable from iteration to iteration. So, you evolve the density through iterations, that is why it is called density evolution. These are the two formulas for Gallagher A. Of course, if you change the Gallagher A rule, these formulas will change. Okay. So, clearly they will change. The density evolution depends crucially on the algorithm you are using. Of course, the all 0 code word assumption and the independence assumptions are vital. Okay. All right, you have to prove them, and there are proofs. Maybe I will hint at the proof later, but right now let us not distract ourselves with those issues. This is the equation. So, essentially what you have done by combining these two is you can write PL as some function of P and PL minus 1. Okay. So, this kind of an equation is called the density evolution equation. okay, and that is something we have derived for the BSc. Okay. So, some function f, I am sorry, is that a question?
What happens if L becomes great, larger and larger?
Yeah, so I am going to talk about it. Okay, so of course, there is run out of time for today. We will pick up from here tomorrow and figure out what happens to this iteration. So, what happens to this iteration. So, that is what will give you the threshold. 0.04 is given by looking at this iteration very carefully. Tomorrow is 4:30. There is an industrial lecture. So, 4:30 we are meeting tomorrow.